Today we're going to be covering the derivative as a function. Now, why do we need to know that? Well, let's take a look at an example. Most things in real life, and the reason why we need calculus, is that any kind of a rate, as in what derivative implies is a rate of change, is not always constant. It's usually changing, it varies. Very rarely do we have a linear kind of graph that depicts a constant rate of change. In reality, things, for example, like an object falling off a building, actually accelerates. So the rate of change, the speed at which it falls, actually increases faster and faster and faster. Right? And if I asked you to calculate the velocity at time equals 1, at time equals 2, maybe at time equals 3. Instead of finding the limit as h approaches 0 of s of 1 plus h minus s of 1 all over h for 1 second, and then doing it again for 2 seconds, and then doing it again for 3 seconds. Instead, what I'm going to do is I'm going to change that 1 and keep it as a variable t, and keep this as a variable t. And let's see what happens then. So we are now looking for the velocity function here as a function of t. Now, some physics will actually tell us that the distance at which a free-falling object falls is given by this equation, the distance measured in meters and time measured in seconds. And with a little bit of magic, voila! I have plugged in the s of t into the limit definition, simplify, cancel, and I found the velocity function, the slope, the speed, to be 9.8t. So at t equals 1, t equals 2, t equals 3, as long as I plug it into here, it'll immediately give me the velocity at those points in time. So now let's take a look at how we had written that. We had written it v of t is equal to 9.8t, which v of t was equal to what we call s prime of t. And this prime right here indicates that it was the derivative of the original function s, or a rate of change, an instantaneous rate of change of the derivative of the function s. Now, if we have a function f of x, therefore, the derivative, we could notate it as f prime of x. We could also denote it as df of x. These ones you don't see as much. D of x, f of x. And this will become important as we move on and we can start deriving with respect to different variables. But let's take a look at a more popular one. So the derivative essentially is a slope where we have a change of y over the change of x, right? But a change of y over the change of x requires 2 points. So taking a look here, for example, change of y over the change of x is some things that we've learned since algebra, right? So it's the slope of between 2 points of a line. In calculus, we are making this change smaller and smaller and smaller and smaller. We're pushing the 2 points closer and closer together until you get the slope at exactly 1 point. And that is what calculus is. So as soon as we take this limit and take that change of x and bring it down to 0, now we have instantaneous rate of change. Okay, we have the derivative. When we do this, I don't know if you knew, but this change of y, this symbol that we use for the change of y over the change of x, is really a capital delta in Greek letters. And so as we take this delta y over the delta x, and we make it smaller and smaller and smaller, infinitely small until it gets really the slope of 1 point, we actually change this to the lowercase delta y over the lowercase delta x. So now this alone is an average rate of change. As soon as we take that delta x down to 0, we make it an instantaneous rate of change. Now the delta is a little rounded like this, the actual Greek letter, but for practicality's sake, we actually write dy dx, the lowercase English letter dy dx. Of course, that is if we're using the letter y instead of a function form f of x. So you can also write the derivative as y prime or delta y over delta x. You can even write it in here as delta f over, I'm going to start using the lowercase, delta f df dx. This is also an acceptable way to write the derivative function. So now let's continue. Let's talk about differentiability. Okay, so what makes a function differentiable? A function we call differentiable at some point a if the derivative f prime of a exists. Now what does that mean? Well, f prime of a, remember, is the limit as h approaches 0 as the slope, right, of between 2 points gets closer and closer to 1 point. What that means here is f prime of a, if this is my point A right here, right, this, if I move this and I make my change of x closer and closer to 0, in order for the limit to exist, in order for this function to be differentiable at that point, you have to consider the slope from the right coming in closer has to be the same as the slope from the left coming in closer. In this case, as you can see, whether I come in from the right or whether I come in from the left, the slope is the same at that 1 point. So this function would be considered differentiable. Now, a good way to think about differentiability, let's take a look at what's not differentiable. So the function f of x is equal to the absolute value of x. This was a little confusing for some in the last problem, so let's review this one. The graph of this function, well, we know all our outputs are going to be positive, so it's going to be above the x-axis. When I plug in 0, I get 0. When I plug in 1, I get 1. When I plug in 2, I get 2. It's linear this way. But if I plug in negative 1, I get positive 1. If I plug in negative 2, I get positive 2. So my graph looks this way. Pretend they're symmetrical. Now, I can redefine this. It's really, really easy to redefine. I can call it the line y equals x as long as x is greater than 0, greater than or equal to, it doesn't really matter where that one goes. And I can redefine this one. This is the line y equals negative x if x is less than or equal to 0. Now, if you take a look at this function, the slope from the right-hand side is a positive 1. The slope from the left-hand side is a negative 1. Therefore, at that point, x equals 0, this function is not differentiable, but only at the point x equals 0. So if I were to write an interval, f of x equals the absolute value of x is differentiable at all the points from negative infinity out to 0, but not including 0, right? And again, not including 0 all the way out to positive infinity. So not including 0 as a parentheses as opposed to a bracket, all the way up to positive infinity. I guess mathematically I would put a u there in union with. So let's take a look at some other functions. This function, as you can tell, a quick way to look, if you take a look at a graph, if a graph is what we call smooth, right? There's no kinks in it, there's no like bends in it, then it is considered differentiable. So in this case, this function is differentiable. Not only is it differentiable, let me actually write it in a different color. Differentiable, there's no breaks in it, so it's also continuous, right? This function right here, whatever it is, it's obviously discontinuous. If it's discontinuous at a point, it is automatically not differentiable. The slope from the left, the slope from the right is not the same, right? So this is not continuous, not differentiable. This function is a good example right here of one that is continuous, because the limit does exist, but the limit of the slope is not the same, do not match up. Okay, so again, it's continuous because I can keep my pencil on here, do not have to pick it up, and I can draw this in one fell swoop. However, it is not differentiable because it has that bend here. The slope from the left-hand side looks like it's negative. The slope from the right-hand side looks like it's positive. This one is continuous, but not differentiable. In this case right here, it's a little bit funky, but it's still smooth. As steep of a drop as it is, as long as it doesn't meet at a point, it's somewhat smooth right there. This is continuous and differentiable. This one again, I can draw this with one line. So this one is continuous. But with these points right here, it is not differentiable. Now again, for all of these that are not differentiable, not differentiable here, it's not differentiable at these points, right? At these points A, at this point A, at this point A, at this point A. So only at these points are they not differentiable. If they ask you if the function is differentiable, they'll usually be a little more specific. Is it differentiable in the domain? Is it differentiable for all points? And so forth and so forth.